Welcome back, Physics 2 people. In this video, we're going to use Ampere's law to evaluate the magnetic field in a toroidal solenoid. You might say, what is that? It is a donut with rectangular cross sections. Okay, so here's what I'm imagining. So from the top down, it looks like this. We're going to have a circle. We'll have another circle. And we're going to have wires which wrap around this shape, and they're going to run so that we're going to have current coming out of the screen from on the top, and then these wires are going to go around. Maybe I should draw some of them. They're going to go around, and we're going to go into the board here on the other side. So you're going to get these wires like that. All the way around this thing. And the current along the top is going to flow like this. So the current is going into the screen in the interior, out of the screen on the outer edge, and kind of over the top. From the side view, if you were to make a cross-sectional slice through, kind of slice this along that line, what you would see is the following. And you would have wires which wrap, kind of come up over the top and then down. Over the top and then down. Like that. So it looks like a donut, but if you make a cross section, you'll see that there are rectangles here. And I'm going to label these radii RA and RB. And it's the same on both sides. So and then, well, we don't really need it for today, so we'll just leave it there. Later on, we'll need to know a formula for the area of this cross section, but we don't need that for right now. Okay, so that's what we have to do. So if I go back to my picture and sort of redraw it, and on the outside, remember, I have the current going into your eye, and on the inside, it's going in like that. Okay, so if you were to draw an Amperian loop in the interior, you would find that there is, in fact, a net amount of current piercing through that surface. So that means you're going to get a magnetic field going around there. And if you grab the wire, you'll see that the magnetic field lines are actually going to run clockwise the way I drew it. Okay, so the magnetic field lines are going to run clockwise like that. And there'll be 0 on the outside. So that's okay. Now we're going to assume, oh, we're going to assume that there are many turns. So many turns that basically these wires are continuously spread over the surface, both on the inside and the outside, even though I know I had to spread them out to make them visible. All right, so then we just do our usual thing. We integrate b dot ds around this loop, and that's going to be mu naught times the current enclosed. Well, each one of these wires carries current I, and it winds through in times. So the current which pierces one of these loops, these Amperian loops, is in times I. So we learn that B inside times 2 pi r, where we measure the radius from the center, equals mu naught n times I. Or the magnetic field inside the toroidal solenoid is mu naught n I over 2 pi r. That's our final result. Okay, so having finished that result and that example, we will next turn our attention to understanding time dependence and the idea of electromagnetic induction. Thank you.